we start with this lecture on layout compaction. Now, the basic idea behind layout compaction is this. You see, we have seen the various steps of physical design. Starting with some kind of specification and netlist, we go through partitioning, placement, floor planning, routing, then detailed physical design. Finally, we create a layout which is nothing other than, as you have seen already, some collection of rectangular shapes. These rectangular shapes may indicate short segments of connections on diffusion, polysilicon or the various metal wires. They may represent transistors, which is an intersection of a diffusion and a polysilicon rectangle, or there can be various contact connections. Okay. So here we talk about layout compaction. Now, layout compactor, what it does, it generates or it reduces the area of a layout at the mask level. Well, compactor is general, it can generate the layout from the stick diagram also, like what I have said, or given a layout, it tries to reduce the area by bringing some rectangles closer to each other. See, the idea is this: you already have the design rules. Design rules specify that your wires has to be of minimum this width, they have to be of minimum this much separation. Now, in a layout you may see that, well, this separation between two features or two blocks or objects are greater than what the minimum design rule constraint specifies. So, you can possibly bring them to closer. Basically, this layout compaction means this: you try to bring things closer to each other without violating the rules or constraints, such that you generate or you get a layout whose area is reduced as compared to what you had originally. Okay. So, compaction is a quite general tool. So, you can use it for a number of things. Of course, area minimization by removing redundant space, what I was saying. Second thing, you can also use it for layout compilation, means starting from a symbolic layout or stick diagram layout, you can directly generate the mask level layout, the rectangles, following the design rules. Redesign means you can have, as I said earlier during our discussion on design rule check, so you can have a phase where you check for design rule violations in your layout. So, once some violation is detected, this layout compactor tool can rework on that part where design rule violations have taken place and can create a correct design which do not have any violations. And of course, rescaling: when we go from one fabrication technology to another, you can use this kind of compaction tool to convert the layout from one to the other. Fine. So, when I talk about compaction, there are a few things: space between the features, size of the features, and shape of the features. Well, normally shape of the feature is predefined in many cases, but in some cases there may be some constraint on the shape of the features as well. So, this can accept some kind of a layout as input and generates the final layout as output. So, let us try to see the problem formulation. So, we are given a set of geometric features M1, M2 to Mn. So, the features, when we talk about, they can be any kind of features. I am just showing them as rectangular blocks without any colors, because I am not showing the layers in general. But what I am saying is that depending on the layers in which these blocks are, there can be several constraints, like of course design rule constraint says that you have to have some minimum width of these lines. So, we assume that those are satisfied, you can also check it basically, but what we are more interested is that what are the separation between these blocks. Suppose you may find that for this one the actual separation is 4 lambda, but our design rule says that it should be greater than equal to twice lambda. So, in that case we can possibly push this rectangle up by 2 lambda. Similarly, let us say this is, we see this is 3 lambda, but again our design rule says it has to be minimum 2 lambda. So, we can again push this to the left by 1 lambda. So, in this way we can create a layout which will be smaller in terms of the total area. Okay. So, there are two kinds of constraints which are specified. One is the minimum feature size. So, for each of the geometric features, this SMI will indicate typically the minimum width, or in some cases also height and width, and the minimum separation between every pair of Mi and Mj. This is denoted as D Mi Mj. The objective will be, given this layout, you try to minimize the layout such that size of Mi, where size of Mi is the size of this after compaction and dist Mi Mj is the distance after compaction, they should be greater than or equal to the minimum value that is specified, okay, for every pair of I and j. This is obviously the problem formulation. This is what you are trying to do. Now, some of the design style specific issues, like when we talk about the full custom design style, it is here where compaction becomes very critical, because the blocks can be located almost anywhere in the chip. So, there is no regularity in the layout, unlike the standard cell where you put everything on the cells and they are already pre-designed. You see, for standard cells, each of these cells are picked from a library. They are already pre-designed and optimized. There is no scope for any further compression or compaction. In a standard cell, the only thing you can compact is rows, maybe the amount of space you had kept between the rows, you did not use that whole space for routing, you can move one row above a little bit. Okay. But for full custom, it is very general. You can have the possibilities of compaction in almost all ways. Typically, after placement and routing, lot of space are left vacant, you have to compact them. So, for standard cell design style, as I have said, the heights of the cells are already fixed. So, you cannot do anything there. So, the height of the layout can be minimized only by minimizing the channel height. So, this is something called channel compaction. For gate arrays, again, because the location of the gates are already fixed, there is no scope for compaction here. So, when you say compaction, generally we do it for full custom design. So, broadly speaking, compaction algorithms can be classified into two types. First is a graph theoretic approach, which are based on minimum distance between features. There is something called constraint graph which can be used, or the concept of virtual grid. Second broad class is more direct. Just along some directions, one dimensional, two dimensional, or something in between, it is called 1.5 dimension. You can move the features and try to carry out compaction. So, let us look into this one by one. So, the constraint graph based compaction, it defines something called a constraint graph. Now, in a constraint graph, every vertex represents a rectangle or a component. and the edges, they represent various kinds of constraints. The constraints types can be two types. One is, they may say something related to connectivity, the two words must be connected to each other, or something related to separation. Now, connectivity constraints, like say, here I am giving an example. Suppose there are two features x and y, and the feature, the location is identified by the middle points. Say along x axis, this is the middle of x, this is the middle of y. The connectivity constraint says that x and y must be within distance s of each other. This s can be 0 also. So, if there is a direct connection, this s can be 0 also. So, if there is a constraint like this, then in the graph we add a pair of edges, one from x to y, other from y to x, with negative weights. The weight of the edges will be minus of s. Minus of s indicates that it is that this x and y must be within this range and they cannot be moved away, because if you move it away, the value of s will increase, and the weight minus h, it says it will make the cost function worse. So, the cost function is defined accordingly. Okay. So, when you make such moves. So, the other kind of constraint is the separation constraint. It says that two blocks must be at least d distance away from each other. So, here you add an edge with a positive weight d. So, in general you will be having a large graph with both positive and negative edges, that will be your so called constraint graph. Okay. Now, the question is, how do we generate the constraint graph? Constraint graph means given a number of blocks, block means the rectangles I am talking about here in this context. So, what are the constraints? Separation, their connectivity and so on. So, one of the very interesting methods of generating the this kind of constraint graph is something called shadow propagation. Shadow propagation means the idea is as follows. Suppose I have the layout with me. So, I am using an imaginary source of light. So, I am illuminating my layout from one side. Okay. Some of the blocks will be generating some shadows, like what I mean is that something like this, like I have my layout here. Let us say there is a block A sitting here. So, I am using an imaginary source of light from this side. So, what will happen if the light falls as parallel rays on this edge, this block A which is opaque will be generating a shadow in this region. So, there can be some blocks in this region also. Let us say there was a block here. So, this shadow will totally cover this block. Okay. Such things can happen, but there is a if there is some block out here, let us say a block B here, this B will also get the light. Okay. Fine. So, the shadow of the feature is propagated along the direction of compaction. Here I am saying from left to right. The shadow which is generated is slowly propagated from left to right. And as I said, the shadow is caused by shining an imaginary light from behind the feature under consideration, and this shadow is extended to both sides of the feature, usually not on the right level. Like here what I am saying is that in general, for a complete layout, so I may consider a feature which is inside in the middle, let us say A. So, for this sometimes I imagine my light to be here, so that shadow will be propagated along this direction, but maybe after that I will be imagining my light to be here. So, the shadow will be propagating in this direction. So, the constraint on all the sides, similarly up, similarly down, they will be considered in all directions. So, whenever the feature is obstructed by another feature, we add an edge. This is the idea, and the obstructed part is removed. This process is continued until all of the shadows has been obstructed and is repeated for every block or feature in the layout. So, I am illustrating with a small example. Let us take this. Suppose we are illuminating this light with respect to a block A. So, we are trying to look at the dependency of the block A. So, we are illuminating a light from this side. This light reaches A, this light also reaches F. But you see, because of the geometry, it does not reach. See, for this there will be a shadow. So, I am extending this a little bit. So, this is the shadow I am showing. The shadow is being extended to B, but the shadow does not touch C because C is hidden by B, right. Similarly, here the shadow reaches D, it also reaches part of E. Shadow reaches G, but does not reach H because H is hidden behind G, but light directly reaches F. So, with respect to the shadow, see, A's shadow reaches where? Reaches B, reaches D, reaches G and reaches E. So, there will be one edge in the constraint graph corresponding to all these. So, and when you add these edges, depending on the design rule, you can also add the weights. So, A and B minimum how much separation it should be. Suppose this is polysilicon, this is also polysilicon, this should be 2 lambda. Similarly, A and D, how much minimum separation? A and E, how much separation? Like this. So, this you repeat for all the blocks and you will be getting all the edges in the graph, right. So, this is the basic idea behind generating the constraint graph. Then we come to something called virtual grid based compaction. So, here we are imagining a grid on the layout surface. So, we are assuming that the components are all attached to a grid. That means, it is something like this. Let us say we imagine some grid lines, let us say in one direction only I am showing, and the components on the rectangles, they are all tagged with the grid. One is like this, one is tagged like this, other is maybe like this. Similarly, here there can be one object like this, one object like this. Right. So, here what I am saying is that here we are allowed to move these grid lines to the left or to the right, whatever is applicable, but when you move it, here all the objects which are attached to the grid, they will all move simultaneously. This grid line, if you move to the left, all these 3 blocks will also move. So, you look at this separation, minimum separation, you see that whether the separation is greater than the minimum permissible. If not, you move it as long as there is no design rule violation. As soon as there is a violation, you stop there. Okay. So, here each component is considered attached to a grid line. The compaction process compresses the grid along with all components placed on it. So, they all move together, keeping the grid line straight. Like, we do not make the grid line crooked. We will see a version later where you can do it. Grid line crooked means, let us say for this grid, so I do not move this, but I move this one a little left, let us say here. So, now my grid line becomes like this, it becomes zigzag. This is not allowed, okay, in this method. So, the minimum distance between two adjacent grids depends on the components on these grid lines. Component means, let us say this can be metal, this can be diffusion, this can be metal, this can be polysilicon, this can be metal. So, depending on them, this separation will be defined. So, you can do a compaction along the x direction, you can also do a compaction along the y direction. So, you can define the wires vertically, which means you are doing x direction compaction, or you can define these grid lines, you can define them horizontally, means you will be doing compaction in the vertical direction. Okay. So, you can do x compaction followed by y compaction or vice versa, both you can do. Okay. So, the advantage is that it is fairly simple and easy to implement. You have the layout with you containing all the rectangles, you just assume the grids and you move the blocks around to align them with the grids, then let the grid lines move as much as possible, you can compact. Okay. But the drawback is that it does not produce a very compact layout as compared to constraint graph method, for example, because you are constraining. So, when you are defining a grid, you are saying that there are 10 blocks connected to the grid. So, either they all move together or none of them moves, but it may be possible that out of this 10, 4 of them you could have moved, but the other 6 you are not able to move, that you are not allowing here, right. So, a very simple example. Let us consider means a situation here where there are 9 such blocks or objects features. So, the separation between them are shown 3, 2, 6, 4, 4, 3, and the distance or separation between these two grid lines are 16 and second and third grid line is 12. Now, you may see that this actually does not show, but these may be some features are such that you can bring them closer together. So, by doing that, this example shows that you have been able to bring DEF closer together. So, now this distance becomes 14. Similarly, GHI also you have moved closer together, this distance becomes 11, something like this. Similarly, when you move in the y direction, you will be imagining grids like this and moving in the other direction, right. So, this is exactly what we do here in case of this kind of virtual grid based compaction, where given a complete layout, which I am repeating, given the complete layout, you imagine grid lines, and as and when required, you align the small rectangles to the nearest grid, then let the grids move with all the attached blocks or objects with it. So, this is how you are doing the compaction. So, here the checking for the design rule is also simple, okay. And of course, this algorithm will be linear in the number of blocks. So, the time complexity will not also be very high, all right. So, this is the method. So, we shall later see means another variation where we do not restrict ourselves to a, you can say, vertical grid. So, grid can be broken and made zigzag if required, okay. This can be one variation. But with this we come to the end of this particular lecture. In the next lecture, we shall be looking at some more methods of layout compaction, in particular the more direct methods, those 1D, 2D and 1.5D. Thank you.